Hi, ladies and gentlemen. In the last sessions, we understood the properties of random variables. We understood the cumulative distribution function, the PDF, and the statistical averages. Now we have to understand stochastic process. So let me start with that presentation. So the speech is organized into your learning outcomes, the definition of stochastic process, the distribution and density functions of stochastic process, the statistical averages, and the concept of stationarity. Then we will see some examples of Whiteson stationary stochastic process and the summary of understanding. So you will learn about stochastic process, then you will learn the first and second order distributions of stochastic process. Then you will learn the statistical averages of stochastic process. Then you will learn the conditions for Strickson-Sons and Whiteson stationarity of stochastic process, and we will see some examples. Now, when we come to the definition of stochastic process, consider a random trial with the outcomes alpha and the sample space say omega. Then consider a time-dependent random function x t comma alpha, that's a function in both the time and the outcome, that is assigned to every alpha the outcome that is element of omega. This xt alpha is called a stochastic process or random process. So that's a function of both the outcome and time. So I have some random trial that has some outcome say alpha, and I consider a time dependent function xt alpha for every outcome, that is x t comma alpha. That xt comma alpha is called a stochastic process. So that is a function of both the outcome and time. For a fixed time, say for a given time t equal to tau, xt alpha, x tau alpha is a random variable. That is, I take a particular snapshot in certain time, then that xt tau comma alpha is a random variable. For a fixed alpha, xt comma alpha is called a sample function. For a given alpha, if you say x t comma alpha is called a sample function. So this diagram describes it very well. See, this is the outcome of experiments alpha 1, outcome of the trial alpha 1, alpha 2, alpha 3, etc., alpha n. This together these form the sample space omega. So associated with the alpha 1, say I have a random function that is x1t, that is this. Okay, say associated with alpha 2 I have another sample function say x2t, and associated with alpha 3 I have x3t, etc. The whole ensemble that is called a stochastic process. And if you take a snapshot in time, this is a random variable at t equal to t1, it's a random variable, this is another random variable x2, and this is the first sample function, this is second sample function, this third sample function. The whole ensemble is called a stochastic process or random process. So it is always understood that the random process is a function of the outcome. So this alpha is always understood. So you can, instead of xt alpha for brevity, we can say x of t. A stochastic process can be written as simply x of t. It is understood that's a function in alpha 2. The first observed random process was from biology, that is from Brownian motion. So scientists put a pose in water and observed through a microscope. He saw strange patterns, strange movement of pollen in water, and there was a first observed random process. And it was Norbert Wiener who later provided a mathematical model for the Brownian motion. This Brownian motion is actually a basis for much of the things happening in the stock market. Many other places also Brownian motion plays a significant role. So why we learn the stochastic process, the communication signals are stochastic process or random variables. That is why we learn stochastic process here. Now, once we understood about the stochastic process, it is very imperative that we characterize them. So we have to understand the distribution and density functions of stochastic process. So let us consider a stochastic process xt at time say t1, x1 equal to xt1 is a random variable, as we said earlier. At time t1, if you take a snapshot of it, it's a random variable. And its first order distribution, fx alpha 1 t1 is the probability that x t1 is less than or equal to alpha 1. Fx alpha 1 t1, there is a probability that x t1 is less than or equal to alpha 1. So this is the first order distribution function. The derivative with respect to alpha 1 will give you the probability density function. So the corresponding density function is fx alpha 1 t1, that's equal to dou fx alpha 1 t1 divided by dou alpha 1. So this is how I compute the first order density function. Now if I take two snapshots, say at t1 and t2, say xt1 is x1 and xt2 equal to x2, if they are two random variables, then I can have a second order joint distribution, that is fx alpha 1 alpha 2 t1 t2, that is the joint probability that xt1 is less than alpha 1 and xt2 is less than alpha 2. So fx, the joint second order distribution, is the joint probability that xt1 is less than alpha 1 and xt2 is less than or equal to alpha 2. So this is a joint probability distribution, and the joint density function will be a second order partial derivative as fx alpha small fx alpha 1 alpha 2 t1 t2, that is equal to dou square fx alpha 1 alpha 2 t1 t2 divided by dou alpha 1 dou alpha 2. So this is the second order density function. You can have the nth order density function. Only thing is there will be n joint events in that. Probability that xt1 is less than alpha 1, xt2 is less than alpha 2, say xtn is less than alpha 2. So and nth order partial derivative will give you the density function. Now once I understand the probability density function, we have to compute the statistical averages of stochastic process. The mean of a random process xt, that is mu xt, that is expectation of xt. Earlier, when we considered random variables, this time dependence was not there. It was simply mu x. Now, since it is a stochastic process, that is a temporal dependence, and mu xt, that is equal to expectation of xt, that is minus infinity to infinity alpha fx alpha t d alpha fx alpha t d alpha, because I multiply this by the this outcome by the probability density function. Here it is a first order probability density function. And the second order statistical average, the autocorrelation of xt is rx t1 t2 rxx t1 t2 xx, meaning that's an autocorrelation function, correlation of xt with itself at two time intervals t1 and t2, that is expectation of xt1 into xt2. So it's a double derivative of minus infinity to infinity, minus infinity to infinity, alpha 1 alpha 2 fx alpha 1 alpha 2 t1 t2 d alpha 1 d alpha 2. This is the autocorrelation of xt. Okay, this is the autocorrelation of xt. Now the autocovariance of xt, that is c xx t1 t2, this is the expectation of xt1 xt2, but both xt1 and xt2 are centered around the mean. So it is expectation of xt1 minus mu xt1 into xt2 minus mu xt2. That will be expectation of xt1 xt2 minus mu xt1 into expectation of xt2 if I expand this equation, minus mu xt2 into expectation of xt1 plus this term mu xt1 into mu xt2. Now this is expectation of xt2, which is mu xt2. So this is mu xt1 into mu xt2, and this is mu xt2 into mu xt1. This expectation of xt1 is mu xt1. So I have 2 times mu x minus 2 times mu xt1 mu xt2 plus mu xt1 mu xt2. So it will be expectation of xt1 xt2 minus mu xt1 mu xt2. And what is this expectation of xt1 xt2? This is rx t1 t2. So it is rx t1 t2 minus mu x t1 mu x t2. Okay. So this is very similar to the earlier equation in between sigma square and mu square. So rx t1 t2 is cx t1 t2 plus mu x t1 mu x t2. Not all stochastic processes can be dealt with easily. So there is a concept of stationarity of stochastic process. We work mostly with the stationary stochastic process. So what does the stationarity say? We say about stationarity in 2 ways. One is a Strickson stationarity or SSS, and the Whiteson stationarity WSS. A stochastic process is stationary in the strict sense if its PDF is invariant at a time shift, like if fx alpha 1 alpha 2 etc alpha n comma t1 t2 etc tn, if this is equal to fx alpha 1 alpha 2 etc alpha n and comma t1 plus e t2 plus e etc tn plus e, then it's a stochastic process that is stationary in the strict sense. That is, the PDF is invariant under time. So it's very difficult to have such a situation because everything is affected by time. Every system is affected by time. So you can have a PDF that is truly invariant under time. So what it says is the PDF is invariant, that is fxx comma t, that should be equal to fx comma t plus c, is something very hard to achieve. SSS is very hard to achieve. But stationarity in the wide sense is more useful and acceptable for most practical cases. So we cannot, in most cases, we cannot meet this very strict condition. So what we can have is a more relaxed condition called wide sense stationarity. So a stochastic process xt is stationary in the wide sense if it meets two conditions. One is that its mean is constant, that is mu x t is independent of time, it is simply mu x, and its autocorrelation is a function of the time shift, that is rx t1 comma t2, that is equal to rx t1 minus t2. If these two conditions are met, then the stochastic process xt is stationary in the wide sense. First condition is its mean is constant, that is mu xt is mu x, and its autocorrelation is a function of the time shift, that is rx t1 comma t2. It is not dependent on t1 and t2, but it depends on t1 minus t2, that is rx t1 t2 if it is equal to rx t1 minus t2 or t2 minus t1 for that matter. Then if these two conditions are met, the stochastic process is stationary in the wide sense. Now, an SSS is always WSS. If a process is strict sense stationary, then it is wide sense stationary. But the reverse need not be true. A WSS process need not be a strict sense stationary process. Now let us see some examples of a wide sense stationary stochastic process. Let us consider a sinusoid with a random phase. Consider this random process xt, that is equal to a cos 2 pi f ct plus theta. Here this a and fc are constant. They are not random, like a and fc are, they are deterministic, but the theta is random. Suppose you go to the lab and turn on a signal generator, a sinusoidal signal generator. This is what is happening. So we do not know the initial phase. Sometimes you assume that you start with theta equal to 0, but this theta may be at different point, like at different phases. Sometimes it may be at pi by 4, sometimes it may be at pi by 2. One can never know where the phase started. So we know that this theta, this random variable, this angle, phase angle theta, which is a random variable, now it is uniformly distributed in the interval minus pi to pi. It can be anywhere from minus pi to pi, and with equal probability. It can be minus pi, it can be minus pi by 2, it can be minus pi by 6, it can be pi by 6. Okay, it can be any angle between minus pi to pi with same probability. So I can say that this theta is uniformly distributed in the interval minus pi to pi. That is f theta theta. This is the PDF of theta is 1 by 2 pi from minus pi to pi. Why it is 1 by 2 pi? Because the interval is minus pi to pi, and it's flat. It's a rectangular one. So the height should be 1 by 2 pi, so that the area under the curve is 1. So everywhere else it is 0. Okay. So it is rectangular with a height 1 by 2 pi from minus pi to pi. Outside it is 0. If that is the case, the mean mu xt of the random variable, that is expectation of xt, that is a minus infinity to infinity a cos 2 pi f ct plus theta into f theta theta d theta, because a is deterministic, fc is deterministic, only theta is a random variable. So you know that this f theta theta is 1 by 2 pi from minus pi to pi, elsewhere it is 0. So this integral, these limits are modified as minus pi to pi. So within minus pi to pi, the value of f theta theta is 1 by 2 pi, which is a constant that is taken out of the integral. And this is a cos 2 pi fct plus theta d theta. Now this mu xt defaults to 1 by 2 pi minus pi to pi a cos 2 pi fct plus theta d theta. Now when I integrate this, it's a sinusoid, it becomes a sinusoid, and this sinusoidal function integrated from over one period, that is from minus pi to pi, it is a 0. So this mean mu xt is a 0. So the mean is constant and is independent of time, satisfying the first condition for WSS. Okay, it satisfies the first condition for WSS because mu xt is 0, it's a constant, so it is invariant with the time. So the first condition for WSS is satisfied. Now let us look at the second condition for WSS, the autocorrelation. Rxx t plus 2 instead of saying t1, t2, I said t and t plus 2. If this is a function of tau alone, we can say that the second condition is also met. Now this is expectation of xt plus 2. So here it is expectation of a cos 2 pi fct plus theta, that is xt. And I replace this t with t plus 2. So it becomes a cos 2 pi fct plus 2 plus theta. Now I can take out this a square because out of the expectation, because this a is a deterministic thing, and this f theta theta, this is I have to multiply this by f theta theta. F theta theta is 1 by 2 pi from minus pi to pi. So this integral from minus infinity to infinity, it is modified as minus pi to pi. And inside this integral I have cos 2 pi fct plus theta cos 2 pi fct plus 2 plus theta d theta. Now this is a product of cosines. It's a cos A cos B form. I can write as a cos A plus B plus cos A minus B by 2. So it becomes a square by 2 pi divided by 2 minus pi to pi cos, the sum value will be cos 4 pi fct plus 2 pi fc tau plus 2 theta. Okay, the sum part a cos A plus B, that will be cos 4 pi fct plus 2 pi fc tau plus 2 theta. And the difference will be this cos 2 pi fct will be gone, theta will be gone. What remains is cos 2 pi fc tau. So this cos 2 pi fc tau plus cos 4 pi fct plus 2 pi fct tau plus 2 theta d theta. Now this cos 2 pi fc tau is not a function of theta, so that I have two integrals. So the first integral will be half 1 by 2 pi a square by 2 cos 2 pi fc tau integral minus pi to pi d theta. Okay. And the second one, it's a you can see that's a cos function in even very even terms. So this cos function, when integrated, it will be a sine function. It will be a sine of even harmonic, sine of sine of 4 pi fct plus 2 pi fc tau plus 2 theta integrated from minus pi to pi, it will be a 0. Okay, so my integral defaults to 1 by 2 pi a square by 2 cos 2 pi fc tau minus pi to pi d theta. This integral will be 2 pi. So that 2 pi will be cancelled with this 2 pi, making it a square by 2 cos 2 pi fc tau. So my Rx t plus 2 becomes a square by cos 2 pi fc tau. You can see that it's not a function in t, but a function in tau alone, the time shift alone. Now you see that this the autocorrelation is a function of the time shift alone and not on the individual and not on the time t. So this autocorrelation depends on the time shift only, so it meets the second condition also. So this process xt is WSS. Now this sinusoid with a random phase, this is a stochastic, that's a WSS. It's a Whiteson stationary stochastic process. Now if this the same random process, if this A is a random, then it will not be WSS. Now let us try that as a second example. If A is random, mu xt will be expectation of xt, that will be expectation of a cos 2 pi fct plus theta. Now this cos 2 pi fct, this bracket is wrong, cos 2 pi fct plus theta is deterministic, so it comes out of the expectation. It is cos 2 pi fct plus theta expectation of A. Now unless this expectation of A is 0, this mu xt is a function of time. It is cos 2 pi fct plus theta into expectation of A. Now this this mu xt is a function of time. Unless this expectation of A is 0, this is a function of time. So the mean is not constant if expectation of A not equal to 0. So the first condition is hard to meet. So let us look at the second condition of the autocorrelation. The autocorrelation is Rx t comma t plus 2, that is expectation of xt plus 2. What is xt? That is a cos 2 pi fct plus theta. So it is a square into cos 2 pi fct plus theta into cos 2 pi fct plus 2 plus theta. Now you can take out this cos functions. Actually, it's a cos a plus cos b by cos a plus b plus cos a minus b by 2 shape. So it is half of cos 2 pi fc2, this is a difference, and cos 4 pi fct plus 2 pi fc2 plus 2 theta, this is the sum part into expectation of a square. Okay. Now you can clearly see that this Rx function, this autocorrelation function, is a function of t also. Not only 2 but t also. Now you can see that the autocorrelation does not depends not only on the time shift but on time also. So this function, the same random function with a as the random value, this is not a Whiteson stationary stochastic process. So the sinusoid with a random phase, that was a Whiteson stationary stochastic process. The random process, the sinusoid with the amplitude random, that is not a Whiteson stationary stochastic process. And when you come to the summary, you understood the stochastic process, you understood the first and second order distributions of stochastic process and the density function also you have seen. Then you learn the statistical averages of stochastic process, such as the mean and the autocorrelation. Then you learn the condition for Strickson stationarity and Whiteson stationarity of stochastic process, and you understood two examples. And that is the end of this presentation. I thank you all.